Welcome again. This is the IABSE International Association of Bridge and Structural Engineering. You see clearly our website, iabsc.org. And IABSE was founded in 1929, and it is nearly approaching 100 years old today. I happen to be very lucky to be the first president of the IABSE. At the heart of IABSE are its commissions, and under the commissions are task groups. They produce documents, webinars, e-learning, and various other outputs that these task groups deliver. And these are actually the core of the activities under the technical committee. And this is the heart of IABSE. I entreat you all to look into the website and to see where you might fit into a task group, where you might want to follow the work of a task group and see if you could participate in them. So the commissions and task groups are really the core of IABSE's activities, and we look forward to encouraging many participants who might be here in our task groups. IABSE has nearly 45 or 50, the number I'm not particularly sure at the moment, but it is more than 40 national groups. For a national group, you need to have only 6 members in that country, and that country can then form a national group, and we're represented worldwide. We have a number of webinars by the national groups, like this national group, the Indian National Group, is having this webinar. Similarly, the national groups all over the world are having webinars, and we're truly a global body. The events that are happening, the Copenhagen event, it will be in April, as you see there. And the symposium in Copenhagen is ready now. The papers are closed, everything is done, and they're all ready to go. In April, we will be having that event. Incheon in Korea is the next one, and the calls for abstracts have actually been closed just recently. And you can see we go all over the world with our events, and the one in Guwahati will be in 2027. It will be on structural failures, cause investigation, resilience, mitigation, and standardization. And I take this opportunity not only as president of IABSE, but more importantly as vice president of the Indian National Group to welcome you to this event, which will happen in 2027. It promises to be a wonderful event, and I hope to see you all there. Similarly, we will be in 2027, the fall event, the spring event in Guwahati, and the fall event will be in Milan. And it will be on shaping the future of structural engineering, human-centered design, sustainability, innovation in the digital era. So save these dates. Today's webinar is before I go to today's webinar, I want to tell you a little about the Indian National Group. The Indian National Group, it was set up in the 50s, and it is working very well. It has its own offices, and it has its own administrative office and so on in Delhi. It also has an arm in Karnataka and Bangalore, and both these put on a number of workshops, events, and recently we had one on ultra-high performance concrete, a workshop. Before that, we had something on steel bridges, and then we also had our annual day recently and celebrated that with a series of lectures on the award-winning Chenab Bridge. A number of activities are taken up by this group in the IABSE, and the Indian National Group. And I hope you will be also, through the national groups, you will also get information about our various activities if you go to events in the website. Today's webinar, to which I welcome you again, is Pushing the Boundaries, a probable world first, launching a 103-meter network arch bridge using a ropeway cable crane. I will be a moderator. And of course, Deepak, young Deepak will be our speaker. He's the director of Force SE. And I want to tell you a little about this company. It was set up by a group of young engineers from IITs. They had no clue what they were doing when they started, but they had a dream and they had a vision. And that vision you see in this innovation that will be presented today as just one of the examples of their exemplary engineering works that they are doing. Most of them are below 40 in that company, and they are very abreast with all the digital technologies and implementing AI, everything in their designs. And they're doing a lot of work, including cable stay bridges, express bridges, and the like. So this is really a story of young engineers today, showcasing their talent and innovation. I happen to be your president, and I have various other hats that I wear. But most importantly, I also belong to Indian National Group. I was a PhD from Imperial College, and also I did my master's in Michigan, Ann Arbor, Michigan. I have a number of projects, mostly in bridges. That's my passion. And I represent on various international and national bodies and so on in our profession. I also have an interest in asset management, which you see, and I'm involved with standardization, number of international, national scientific and technical committees, editorial boards, and the like. So my company is called Consumer Consultancy, and we also have a huge passion for bridges, I must admit. Our speaker today, Deepak, young Deepak, as I would like to refer to him, and he is the co-founder and director of the company Force SE Private Limited. He is a gold medalist for his BTech and MTech degrees from IIT Mumbai. He has more than 15 years of professional experience, and he has extensive expertise in design and detailing of long-span bridges, elevated viaducts, and special structures, including what you will see today, a network arch, and balance cantilever, cable stay, etc., different types of forms of bridges. Deepak is proficient in the design of both steel and concrete structures and has been instrumental in delivering several landmark bridge projects across India. Before I hand over the mic to him in a bit, I want to tell you about IABSE. Some more features about IABSE is that it addresses all types of structure. It's not only bridges. We deal with every type of structure in the built environment. We deal with all materials, be they ultra-high performance concrete, stainless steel, CFRP laminates or concretes and steels and the like, and timber, and in all types. We deal with all types of materials. All aspects of construction processes, different types of construction methods, processing. We bring out a number of documents on the same. And we are having members from more than 100 countries. We are truly a global body in our profession of structural engineering. The IABSE mission is very clear. The International Association deals with all aspects of structural engineering, the science and art of planning, design, construction, operation, monitoring and inspection, maintenance, rehabilitation and preservation, demolition and dismantling of structures, taking into consideration technical, economic, environmental, aesthetic, and social aspects. The term structures includes, as I said, buildings, bridges, and all types of civil engineering structures composed of any material. The IABSE has many objectives key to our profession, including issues like ethics and dealing with sustainability recently and addressing these matters with its own task groups and participating in global networks on the same, for example, like the Globe Consensus. Having said that, the heart of IABSE is in its national groups. Today is one such event of a national group. And I again request you all to learn, contribute, grow with IABSE by joining it. It brings out a premier journal, which is unique, the Structural Engineering International Journal, SEI, which addresses both research as well as practical projects. And in that sense, it's a unique journal for India, for the world. And all our webinars are free. We have a new academy. We have an e-learning board, in which a lot of material is available to everyone and anyone, lots of videos, learning. We have a translator across different languages for technical words and translations to translate different books and papers, etc. You can use that tool on the website. We also have a large amount of e-learning resource, a repository of a lot of knowledge, and we have a special focus on the young engineers. We have special prizes for young engineers. They're able to network with various experts in the field, and we have speed networking sessions, and the young engineers have their own YEC, the Young Engineers Committee, YEC. They have their own program and run their own events. Here too in India, we have a number of programs for young engineers, including sort of field visits and the like to bridges and buildings and stadia. Again, I tell you that there is a new offering coming from IABSE, which is the IABSE Academy. Watch out for it. We are coming up with two offerings very soon in this year, in the coming year. is somewhere around Jan, Feb. You will see two. One is a bridge diploma, and the other is a forensic engineering diploma. You can take them as part, you can take the modules as part and pay by part, or you can do the whole and earn a diploma by submitting a thesis. And that will have CPD and a sort of a global stamp and badge of IABSE. So we will be launching many such, many such diploma programs in our IABSE Academy. Watch that space and join and learn from it. We also have an awards function every year. I hope structures from India, just now Chenab Bridge won an award. Deepak Singla got the award for Early Career Prize. So India is getting lots of recognition, and I would like the youngsters from India who are in this program to especially participate and grow with IABSE. Having said that, anyone who's here from all over the world, please do participate in IABSE activities. It is a unique body, and I entreat you to join and participate. The talk today is, of course, about a very unique type of bridge. I won't get into much detail. I'm just giving you a teaser here of the difficult terrain in which it was to be done. Imagine a 103-meter span suspended midway across a 50-meter deep gorge, hanging on 2 points from a ropeway cable crane. What sounds like an impossible feat became reality in Mizoram, India. It's a state in the northeast of India, where one of the country's first steel network arch bridges was launched using a ropeway cable crane, a probable first in the world of bridge construction. The operation also set a probable world record for the heaviest point load, 220 tons, ever transported over a cable crane. Now, Chenab Bridge is similarly built with the biggest cable crane ever done in the world, probably, the Chenab Bridge, Arch Bridge, but that was built piecewise. Here, in this case, the whole bridge was launched at one time. That's the difference. It's located very close to the Aizawl airport, and the bridge site presented a lot of challenges. It's flood prone, it's in a very high seismic zone, very deep gorge from which we cannot get any staging, and the conventional erection or launching methods were unfeasible. So a lot of innovation was put in by Force SE to come up with a system and make it work, and you will see in this presentation exactly that being presented. So Deepak, I would say you will cover all the engineering, the issues and the launching. So over to you, Deepak. Let me get out of this and unshare. Okay, Deepak, it's stop share. Back to you, Deepak.
Okay. Thank you so much, Harshvardhan sir, for the wonderful introduction and giving me the stage. And I'll also like to thank IABSE for giving me an opportunity to tell the story of this amazing bridge. So I will start my presentation and share my screen. Yeah. So I think my screen is visible.
Yes.
Yeah.
Yes.
Okay.
Yes.
Okay. So look at this picture and imagine when this bridge was being launched. So this is the image of the 103-meter span network arch bridge, weighing around 440 tons, hanging on two ropes over the 50-meter deep gorge, in middle of its journey from one abutment to another. Imagine you are the designer of the bridge and the complicated system that takes it through from one end to another. And this is the first time that you have designed such a system. Before that, you have never worked with the ropeway systems and cable cranes, and that you have designed everything from first principles and common sense. And now you are also operating all the winches that make this complex system work, and the bridge is approaching the midpoint of its journey, the point of the maximum load for the entire system, the point of max q, as it is called in rocket science, the moment of truth, and if the bridge will pass through or not. So now the good thing is that it passed through nicely as per the plan, and the entire operation happened flawlessly in around 6 hours, probably setting two world records. Firstly, this would be a probable world first launch of a complete bridge using ropeway. And secondly, probably this is the heaviest point load, around 220 tons ever transported by a cable crane over a ropeway. So how did we make it happen? Let me take you through the story of this bridge. Why network arch was chosen over other forms, basic overview of the design process, why such a launching scheme was used, how was it designed, the testing procedures that were followed, and we will wrap it up with a video of the launch. So this is the tender proposal. The proposed bridge was a 100-meter span semi-through type steel thrust arch bridge with vertical hangers. And the tender was floated by Public Works Department of the Mizoram state, and they wanted the bridge to be an iconic gateway for the city of Aizawl, as it will be a link between the airport and the city. However, after securing the tender during detailed design, it was realized that the foundation was resting on weak shale rock, which was prone to scour. And the river was also prone to flash flood risk at least 2-3 times a year. And the founding level was also below the HFL of the river. So this really made the initial scheme unfeasible because the thrust arch would exert a significant force on the weak shale rock. And secondly, the foundation will be highly prone to scour and might fail. So in this image, we can see this bridge. So this was the existing one-lane Bailey bridge, which was being used before the construction of the current bridge. And this is an old Bailey bridge which had failed due to again flash flood. And like this is a pier of a bridge that was being constructed before the current bridge, but it had to be abandoned because the rock below its foundation had scoured. So yeah, so if we see this next picture, we can see the foundation, and and over here we can see that the river has scoured below the foundation. So now, since the initial proposal was not feasible and arch form was mandated as per the contract, and the bridge had to be aesthetic, we looked for options and zeroed on the most advanced form of arch bridges, the network arch. Though we had never designed it before and it had never been constructed in India when we started the design, we pursued the network tied arch because we found the form to be very aesthetic and structurally efficient. So this is the GAD of the current bridge. It is 103 meter long, slightly longer than the initial proposal of 100 meter. It solved all the problems that the initial proposal was facing. Given the tied arch form, no thrust forces had to be anchored in the shale rock. And secondly, the founding level came way above the HFL of the river bed and away from the river influence zone, so that scour would no longer be a problem. Also, a basket handle type form was chosen to make it even more aesthetic. The bridge caters to 2 lanes of traffic along with footpaths on either side of carriageway, and it is designed for 385 tons special vehicle class loading as per the Indian standards. It has 28 number of cables in one plane. The notable feature about this bridge is the very slender arch that you see over here. So for a span of 103 meter, the thickness of the arch at middle is only, it is a box section of only 700 cross 700, made out of 25 thick plates of Fi 350 MPa. And the overall weight of the steelwork comes around to be 440 tons. So why is network arch so special, and why is it better than arch bridges with the vertical hangers? So why do they have a structural advantage over the traditional arch bridges with vertical hangers or a spandrel type? So let's start with engineering basics. Materials are very efficient in load transfer when the loads are transferred axially rather than via flexure. And arches are very efficient system only because they are supposed to transfer loads primarily axially. Now, Bert Witt, who is a father of modern network arch bridges, sadly he is no longer in this world, identified that when arches with vertical hangers are half span loaded, the loaded side arch and the tie, yeah. So the loaded side arch and the tie, it happens to deflect downwards, and the other side happens to deflect upwards, and the arch tend to sway in the horizontal direction. So when this happens, a lot, very high bending moments are created in the arch and the tie itself. So he figured out that if the hangers are just inclined in one direction, the sway and deflection of the arch are restricted, and so are the bending moment in tie and arch. The arch starts to transfer load axially the way it is supposed to be. So now we see once the hangers are inclined, the arch is no more deflecting. The arch is nearly at the same place and it has primarily axial forces. So, but now this inclination of hangers will not work when the load is applied in another half of the span. So if I just remove this load and if I apply load in this half, and I keep this inclination of hangers, it will not work. It will not solve the problem. So for this side, I have to, mirror these hangers. So I will have to install hangers in this direction. So now we see if we have hangers in both the direction, we get a network arch. So a network arch bridge is an arch bridge in which the hangers intersect at least twice. A system where the arch has minimalistic bending moments and primarily axial forces. Hence, the arch section can be reduced drastically, leading to economy and aesthetics. It offers primarily three advantages. First is the optimized load distribution, which I explained. Second is reduced material consumption. The superstructure cost can reduce by around 30 to 35% compared to arch with vertical hangers. And aesthetic appeal. It offers aesthetically pleasing and modern design. So now let's go how the geometry of the bridge was chosen. The height of an arch should be normally 15 to 20% of the span. So we chose to be in middle and chose 17 meter. The deck cross section was governed by the tender requirement, and the span was finalized as explained previously to keep the bridge out of the scour area. And basket handle shape was chosen for additional aesthetics. So now for the hanger arrangement, what hanger arrangement to choose, let me explain you the ideal arch loading. So to achieve minimal bending moment in an arch, the line of thrust or the axial force should ideally be aligned with the center line of the arch. And that only happens when the loads are uniformly distributed and applied radially. So for example, in this case, if we have kind of point loads, these point loads should be uniformly distributed and they should all be pointed radially and kind of merge on the center of the arch. And if we have a UDL kind of thing, then again, it should be uniformly distributed and pointing radially. If this happens, it will ensure predominant axial compression rather than bending. So the ideal hanger arrangement, it can be achieved by installing hangers in such a way that their angle changes from one end to another, so that the resulting force in the hangers act uniformly and radially on the arch. So basically, if we see here, what we did is like, if you see this hanger in this plane, basically the hangers change, the angle changes from near vertical to like very slanting. And similarly, the other side is the mirror of it, again vertical to changes to near slanting. What it does is that the intersection of these hangers is typically, if we join the intersection of these hangers, This will be the typical line of the resulting force in the hangers, and these resulting forces will tend to go towards the center of the arch. And when we do that, the arch will primarily have axial forces which will be aligned with the arch shape, and the bending moments will be highly reduced. So regarding the analysis of this bridge, I will not go into analysis and the design in the depths of analysis and design because that will take a lot of time. So the analysis was done in so the arch was modeled and analyzed using sophisticated software, and the connection design was done using idea statica. So regarding design of the bridge, the loads on the bridge were applied as per Indian codes, and the design was done using Indian codes and Euro codes. So at some location where Indian codes might be silent, Euro codes were used. So an arch as a predominant compression member must be carefully analyzed and designed to ensure its stability under compression loads. Like steel arches are particularly vulnerable to global buckling phenomena, which can occur both in plane and out of plane. So the Eurocode offers two methods for design of compression members. The first is the substitute member method. The concept of the substitute member method is applicable for members with uniform sections subjected to uniform axial forces. So it is not really practical to use this method for network arches, since network arches ideally should have varying sections due to the varying forces. And the second method that is offered by Eurocode is the UGLI method, which is the equivalent global and local initial imperfection method. So UGLI method is an advanced method. This can be used for varying section structures. An equivalent, unique, global and local imperfection is basically an equivalent imperfection that has the shape affine to the form of an elastic buckling mode. I will explain this in the further slides. So it includes both the global and local aspect of the verification of stability. Yeah. So the first step in finding the imperfection is to get the buckling shapes and calculate the elastic critical buckling load using eigenvalue buckling analysis. So this is the first buckling mode of the arch, which is out of plane. And the image on the top is the deflected shape of the arch in the first buckling mode. So the unique global and local imperfections are calculated using the elastic critical buckling load as per the codal formulas given in Eurocode. And these imperfections are then applied in the model as deflections with the imperfection shape corresponding to the deflected shape of the buckling mode. And a second order analysis is then done to get the second order moments for the structure. So basically, if you see the shape of the imperfection that has been applied over here is matches with the shape of the deformed structure in the first buckling mode, which is like very important for the UGLI method. So now since I have covered the key concept of the design, I will come to the erection problem, the real problem. So now once the bridge was designed, the question arose how to erect it. So this is the Google map image showing the location of the bridge. You can see there is a very deep gorge over here, and then there are hills on both the side, and they were like the slope was very high, and there was not even space to erect this bridge. So to erect this bridge, basically we had to cut a portion of the hill and make space for erection of this bridge. And this over here is the existing Bailey Bridge that was used before this bridge was erected. So Normally, network arch bridges are erected at place, where they are supposed to be finally. They are erected at place on temporary formwork, or as can be seen in this image, or they are fabricated at some location and launched at place by floating over barges and then lifting in place using cranes, as can be seen in this image. Or it can be erected on one side, simply if I draw this, like I can erect this bridge on one side, and I can put on formwork here, and then I can just roll over the bridge over the formwork. So these are the three methods available. So all the three options were clearly not possible in this case, because like we could not really install formwork over here and erect the bridge on the formwork, because the river was prone to flash flooding, and like when it will happen, there is no surety of it. So any formwork installed might wash away during construction of the bridge. And secondly, same problem persisted with the having formwork and rolling the arch over it, because that can have the same fate. And thirdly, the depth of the gorge was very high, and the low water level, which was for maximum time in the year, was and the draft was very less for any possibility of fabricating it somewhere and then floating it over a barge. So then, what is the solution? So this is the solution that came to mind. So this is the actual sketch that I drew. Erect the arch on one side and transport it over a ropeway using a cable crane. Now there are two problems to this solution. First, we could not find a reference of this method being used for launching a bridge. And secondly, I personally never had worked on or designed a ropeway and cable crane before. So after thorough research, it seemed like probably this will be the first time bridge is launched this way. And it might be also possible, like this might be the heaviest load that has ever been transported over a ropeway. So I was asked this question again and again. How did I know that this will work? And even some people said it will not work, but I held firm that it will work, because I have a philosophy that any problem, at least structural engineering problem, can be solved if it is approached with common sense and first principles. So I learned about ropes, pulleys, winches, and used first principle to come up with the final scheme and designed all of these components. I will break down the component to help you understand better. So this is the final scheme. Over here you see the 60 mm main ropeway cable. This is the main element on which the cable crane moves, which lifts the arch. This small thing over here is the cable crane. It lifts one end of the arch, this end of the arch, and it can move it up or lower it down. And it has three components. The first, the trolley that moves on the main cable, and then there is a upper lifting beam which connect the two trolleys on either side, and third, there is a lower lifting beam which is here. I will show this in detail in later slides, which supports the front end of the arch and is lifted up or down by the upper lifting beam. So then we have winch one cable over here, and the winch one. So the job is this winch one cable is to hold this trolley in place. So because if I don't have the winch one cable and I load the trolley, it will tend to move forward, and that too in an uncontrolled fashion. So for having a controlled launch, this had to be restrained with the winch one cable. Then there is a winch 2 cable, which is over here, and here is the winch 2. So the job of this cable is to actually lift the arch. Then there is a winch 3. Its job is to pull the arch forward. If in case I release the winch 1K restraining winch cable and this trolley moves forward, there might be a possibility that the arch might be lagging behind. So we had a winch 3 cable to pull it forward. Then there was a winch 4, the stopper winch. This is not visible in this figure, but it was it was on the other end, and it was just the mirror of winch 3. And it was primarily a safety winch, and its job was to stop the arch if it started to freely roll forward. But no such requirement arise during the operation. Then there were two other winches which are not really visible in this figure, but they were connected to the front of the arch. So let's say there was one winch here and then another winch there in transfer direction. And their job was to stabilize any transverse oscillation of arch during the transport due to wind, if in case they occurred. But again, the arch was very stable during the launch and the requirement did not arise to use them during the operation. There are saddles at top of tower. So over here we have saddles, and their main role was to provide support for the 60 mm main rope. It was going through them and provided them a frictionless support. So the tension in the rope would remain constant. And then there are these towers. So again, their main role is to primarily take the vertical component of the cable tension to the ground. And there is another tower. So this tower is 30-meter high, and this tower is 10-meter high. And now the question arises, like, why these towers have different heights? And I will answer this question later on in the upcoming slides. And at the bottom of the tower, we had pin supports, again, not really visible over here. So this was kind of a pin support. And the pin supports were provided at the bottom of the tower. So because I just wanted the tower to carry axial forces, no bending moments, because I wanted to economize the design of the towers. And the towers were stayed back using these stay cables, which were again connected to the saddle. And there was one arch bottom support trolley, which again sadly is not visible in this picture, but it was back. It was supporting the other end, and the trolley was moving. The trolley moved over rails when the arch was launched forward. So we'll see that again ahead. And these are the two anchor blocks which were used to anchor the 60 mm rope and the stay cables. So this is the bridge bridge during its transit. We can see this is the 30-meter tower, and this is the 10-meter tower. It's not really completely visible. These are the receiving platforms for the arch. And this over here is the cable crane, which moves on the 60 mm rope. This is the trolley. This is the upper lifting beam. This is the lower lifting beam. And these are the lifting ropes. So this over here is the cable crane, and this upper part is the trolley, which was moving on the 60 mm ropes. So 60 mm ropes were over here, and this trolley was moving on the 60 mm ropes. And there were 8 ropes, 4 on either side, which you can see over here, 4 on this side and 4 on that side. The system was pinned in such a way that the upper lifting beam was always vertical, no matter what the inclination of the trolley on the rope was, because when the trolley will move on the rope, its inclination will continuously keep on changing. So so it was pinned over here, and so that even if the trolley is like this lifting beam is always vertical. And yeah, so below the trolley is the upper lifting beam, and this is the upper lifting beam which is connected to the trolley, and below these are a set of pulleys, and the lifting winch cable was passing through these pulleys from here to here, and then it was making many turns, and then it was anchored over here. So by pulling the lifting winch rope, the distance between the upper lifting beam and the lower lifting beam could be adjusted. And the tie of the arch was resting over here and over here, which we can see, like this is the lower lifting beam over here, and the arch is resting over here and over here. And these are the lifting ropes, and this is just one single rope which is going to the winch, to lifting winch. So we had used multiple sets of pulleys that you see over here, so that the load in the lifting winch was less than 15 tons. And we had used 20 dia wire ropes to lift the arch. So basically, all the 220 tons, the load that was here was the arch was transferring to the lower lifting beam. The lower lifting beam was through these ropes, the multiple falls of them was transferring to the load to the upper lifting beam. The upper lifting beam was transferring the load to the trolley, and the trolley was transferring the load to the ropes. And the load in this one, so though we were lifting this around 220 tons, the load in these ropes were restricted to 15 tons, less than 15 tons. And also there is a set of pulleys in here, which is not really visible. And through these pulleys, the rope connecting the restraining winch was connected. So this is the restraining winch rope. It was connected to pulley over here, and this was a pulley on the saddle, which was on the tower. And again, there were multiple falls to limit the force in the rope. So the winch one cable was used to restrict this trolley from moving ahead and for a controlled release, and winch 2 cable was used to lift the arch. So moving ahead, this is the saddle. Here we can, so this is the saddle. So these are the 4 guides for the 4 ropes. Over here we can see there were guides in the guides made in this shape for the ropes, and below these guides we had installed PTFE sheet. The rope was here, so that basically that same tension would be maintained in the 60 rope. And the pulley over which the restraining rope was going, as I told you, was housed in here, which is like visible here. And these are the points where the tower stay cables were connected to the saddle. The saddle was basically connected to the tower. So this was connected to the tower. So these are the tower legs that we see here. So saddle was connected to the tower, and the stays were installed over here. So over here we, so over here, this is a picture of the tower pin support, and this is the picture of the bottom support trolley, which I was talking about. So it was placed at the below the bearing location of the bridge, and it was moving on rails. So back end was moving on rails, and the front end was lifted using the crane and pulled forward. Yeah. So the tower height difference and how the system works. So I think I have explained about how the system works, how the restraining winch and the lifting winch work, but I will now explain why the tower height difference was there. So basically, let's say if I have maybe this is my god something. Yeah, so if I have this tower and this tower, and I have a rope over it, and if I have, let's say this is a trolley, which is kind of a roller, and I hang a load below it, and I just release it. Basically, this load will move forward, this trolley will move forward, and it will, the rope will form a kink since a point load, and it will come in the middle and stop. It will not move forward. So if we have to move it forward, we will have to pull it. And the maximum naysayers that I face, they had this concern only that the arch will not go ahead. It will be stuck in the middle. It will not go ahead. It will be stuck in the middle. So the solution to this that I found is like, if I make towers with different heights, so then my main rope will be inclined like this. So if I have a load, the trolley, and I put a load, so then the lowest point might be here, not here. So whenever I put a load, it will form a kink. So if I put a load here, the kink will be like this. And this, if we plot this kink will have a kind of profile like, like this. So the lowest point will move in this profile, and it might reach here. So I made the differential height of the towers so that my arch could be like, we had a receiving platform here. So I made sure that the lowest point was like slightly inside my receiving platform. So arch could be safely received. And yes, it worked wonderfully. So basically, what we can say is that it is a gravity assisted launch. Like there was no need to pull the arch from this end. What we need to do, like as I said, if I put a roller and a load over here, it will have a tendency to move forward. So if I have something to restrain it over here and release it slowly, it will move forward slowly, and it will be gravity assisted, and it will reach where I want it to reach. The other thing over here is like, yeah. So if I have this tower and again this tower and I have this, and when this load will move forward, as I said, my profile of the lowest point will be like this. So if let's say my arch was suspended from here, and when this move forward and this move forward, basically this will come downwards, its height will reduce. So I had to constantly adjust the height of this lifting ropes using winch 2, so that when the arch was moving forward, it was not moving downwards, else it will continue to move downwards. So both the winch 1 and winch 2 had to be more or less simultaneously operated. So for you release winch 1, the arch move forward, you pull winch 2, so that it again comes up. Had to be done simultaneously, else the arch will not stay horizontal. So at the end of it, I will be showing a video over there. You can see like you can see the arch. Though the winches were kind of run simultaneously, you will still see some slight adjustment that are being still done to keep the arch horizontal. So coming to the launch analysis. So the launch analysis was done using a very simple model. This is the simplest model that you can have. And this is the one I use. The 60 rope was modeled using cable element, and the saddle and the tower were modeled using pinned roller supports. So the front cable, this, and the back cable, so it was a pinned roller support, and the front cable and the back cable was attached to it. and the load was moved forward in steps, and the load in the main cables, restraining cables, tower stays, and the deflections were calculated from this model for each step. Like this model can give you everything that you need. Just delete. So yeah. So this is like the how the load was moved incrementally, and I could measure all the tensions and the deflections using this model. So coming to the testing procedure, the entire system was thoroughly tested before the actual launch. It took around 1 month to complete all the phases of testing and correcting issues that were faced. The testing was done in following phases. First, the unloaded cable crane was moved from abutment A2, the 10-meter tower, to abutment A1, 30-meter tower, and back multiple times. So this is, you see the first phase where we are moving the unloaded cable crane. Then we had a 50-ton test load. It was again moved from A2 to A1 and back. Then we had made a kind of tank with steel plates, again very light composite, and it could be filled with the soil, saturated soil, to mimic the weights. First, we tested the 100-ton, made a 100-ton test load with it, and tested the entire system. And then we increased the load to 220 ton, matching the actual load that had to be carried that day, and was moved from A2 to A1 and back. So this is the small video. There was no issue during the launch, and the system behaved more or less like predicted by the analysis. The entire launch was completed in 6 hours as planned. And this is again as a small compiled video of the launch. Hope you guys enjoyed. So I'll play it now. Where do we start? So this is the picture of the complete bridge after load testing, and it is open to traffic now. And it has been highly appreciated by the local community, and they take a great pride in it, and it looks so beautiful. So this is the end of my presentation. I would like to thank all the stakeholders of this bridge, the cooperation and understanding of whom made this bridge possible. Special thanks to all of you for being patient listeners. And now I'll give the charge back to Harsha sir to take the discussion ahead.
Thank you, Deepak. We have some questions in the question answer box. You may receive some more. Thank you for that wonderful presentation, Deepak. It was very interesting to know how you innovated, how you tested, how you actually executed at site with full responsibility and confidence. It is a wonderful piece of work done in a difficult situation, a difficult circumstance, and with so many site constraints. We do appreciate your team's efforts. It's not that everything has to be grand and huge and magnificent and size, but it is also to do with the complexities, and innovation comes in everything that we do. And
Yeah.
here is a case where young engineers have got together and created something which a unique solution for that site, putting aside many other almost unworkable solutions, and then doing the engineering, doing the design engineering, doing the construction engineering, and doing the testing of all the components, and then verifying the entire bridge after it was built as a network arch bridge with proof loading, I mean, with a full load test, as you must have done.
Yeah.
So, congratulations on this wonderful work. I feel proud that you are doing such things in your company.
Thank you
Let
so much.
me ask now the questions that you have seen. You have 8 questions, Deepak. I would suggest you start straight away. You can take Hegde's question. You open the question answer box.
Yeah.
Before
So
you start, I just want to reiterate to the audience that this cable crane is a full structure launch. It's not a piece. Cable cranes invariably are used across large crossings, large spans to take elements, like we had done in Chenna Bridge. Here, where's one of the largest, or probably the largest cable crane used in the launch of the Chenna Bridge for its various elements, modular elements, bit by bit. Whereas here we have taken the whole bridge across. So therefore, it's a little different from, it's the same cable crane concept, but differently used with the wonderful safety features that you could build in. So over to you now. First question, Hegde's question. Deepak, what is the significance of hangers intersecting at least twice? Why not once by changing the stiffness of hangers? The concept of the Peartweed's network arch concept of
yeah.
two crossings. Why?
Yeah. So first, I'd like to tell this is not really my statement. That is how Pertwee defined a network arch. So that is his definition. And what it does is, like, the more hanger crossing you have, the more stiffness of the bridge you increase. So basically, it will help you to distribute the loads much better, and the tie will become lighter, and the arch will again become more lighter. So having, like, just one single crossing doesn't really help much. And so if you tend to arrange, like, hangers and do some analysis, you always end up getting two or more than two intersections.
What about how do you choose the angles of the hangers? Again, Venkat is asking the same question to
Yeah.
you again. A question again to you. Yeah.
Yeah.
How did you choose the
So,
angle of the hangers as
so
you did?
basically, we had experimented with the hanger angles also, and there are few research paper also which give the optimal hanger angles, and how they should be planned. So the scheme that we had used also came from a research paper from one of the student of Pertwee only. And he had explained, like, when hangers are varying from like, kind of near vertical to some 30-degree or something, and you do some if you work with that, eventually you'll always get better bending moments. And the important thing is, like, hanger arrangement can also be parallel. Like, we have varying angles. If you see, our angles are not constant. So if you have you can also have parallel hangers. So the problem with the parallel hanger is, like, they tend to have compression. Like, one of the biggest problem in network arch is, like, in under, like, nearly no loading condition, you should get a compression in a hanger, because hanger cannot take a compression. So if you start getting a compression, then you have to get into, you have to eliminate that hanger, do the analysis again. So that might, that problem can become unsolvable. So you always, there is a range that you follow kind of, and experiment with that, some plus minus, to get the optimal angles. So there is not
I,
exactly like specific written that this is in this angle you choose, but you play with it.
I got you. So
Yeah.
basically, it's a trial and error optimization that you must have
Yes,
followed to get
yes,
the
yes,
various inclinations in order.
yes, yes,
Hopefully meeting at the common center as you would have tried to have done. And there
yes.
is sufficient body of research that you can share with others or give them the clue if they want that
Yeah,
information.
yeah.
Wonderful. Okay, then can you tell the reasons why you did not put lateral strut in the arch?
So basically, like in the arch, we have the little bracing. I think behind you only. If people can see the arch, they can see the X bracing, which is there. So that
Yes.
X bracing serves a purpose of the
No, he what he
lateral
probably
supports.
means is what he probably means is where one X begins, the other one starts, X after X.
Yeah,
At that junction, you don't have a lateral tie, you don't have a
yeah,
kick. So that's probably the question why you avoided that because
yeah.
it added
Aesthetics.
out of plane stability. Yeah, go ahead.
Yeah, so it was done for aesthetics.
Okay.
So this system, again, this is a system of triangles. If we see, a system of triangles is stable, and this works pretty well. And somehow we thought that this looks quite beautiful. I have some pictures which are taken below the bridge, and if we see these X, they look
So it's aesthetics, more or less
yeah,
aesthetics
yeah, it's
governed,
aesthetics.
and
Yeah.
you had to do it through design. It would have been an option to put a kicker lateral also to increase the out of plane stiffness. Should you have needed it, you probably didn't need it in your through your analysis and section choice.
Yeah, yeah, yeah,
One thing I note, of course, is that your sections are quite slender, 25 thick, 700, 700. That's quite a slender section. You would
yeah,
not have been able to do it had you not adopted a network arch bridge, I think. The
yeah.
network arch bridge allowed you to get lighter sections both for the top chord as well as the bottom chord.
Bottom chord. So yeah, so I would just like to add one thing over here, like part weight no, point term, like slenderness of a bridge. So that is like if you add the thickness of the top chord and the bottom chord, and you divide the span by that number. So that is kind of a slenderness of a bridge. So for this bridge, the slenderness comes to around 80, and the like the thinnest network arch that has been designed for that number is around 100.
Right, right.
Yeah, so they
Okay,
tend to be
Jack.
very slender.
Right. So it is a slender system that you have, yeah, by that formula. Jack Erzikuran has asked, wow, nice use of mechanical advantage to use multiple 15-ton wire rope to accommodate the 240-ton DC. So he's
Yeah,
appreciating the fact that you use multi-sheaves of pulleys to bring
yeah,
down the tension. So you could bring it down the diameters and you could bring it down with the controllable sizing and loads. So you
yeah,
240-ton was moved by using only 15-ton main wire
yeah.
capacities, which is quite appreciated by him. Yogesh Chaudhary, what was the cost comparison between a normal arch structure and erection and the structure that is erected now, your structure, and say a normal arch? Would there be a commercial difference in cost, 20% difference, 10% difference? A normal arch without a
So
network arch.
no, I
Say,
think what he is asking, like he's asking comparison of the cost of the main bridge and the enabling
okay, the
structures that we
enabling
had to
works. The
enabling
cost
works
of
that
the
we had to
enabling
do.
works all put
Yeah,
together
yeah,
to the cost of the how much is percentage of it was in the
yeah.
temporary works.
So I can say like it was around 50%, maybe 50%, or I'm not like I never discussed this in detail with the contractor, but yeah, it was costly. But like there was no other option that we could choose. And the good thing about it, like all the design, everything was designed by me. All
Why?
this enabling works was designed by me. Nothing was imported from outside the country. all design was
Right.
done. So effectively, in this bridge is a product of three friends. So the contractor, the designer, which is me, and the fabricator. We all are three friends, like nearly same age group. And so I did the design, the fabricator fabricated it, and so we were able to reduce the cost a lot because my focus was always on having optimized sections.
We
And
have lots of questions, yeah.
yeah, another
So
funny
put
thing.
answers as fast as possible.
Okay,
So
okay.
Dick McSweeney asks, hello, thank you for the really interesting presentation. Some questions from me. What was the maximum tensioning used for relative to the maximum breaking load of the cables? Probably the factor of safety. What is the service life of the bridge? Which company provided the cables? Were they all sourced in India, etc.? And
Yeah,
that
yeah.
type of question.
Basically, like the 60 rope, the main rope, it had tension of around 100 tons. Its capacity is 180 tons. The other ropes, as I said, were 24 ropes. Their capacity is around 30 tons. We had restricted maximum load to around 15 tons. The service life of the bridge is 100 years, and the like I don't know exactly the company that had provided, but it's a standard. The ropes are standard products, and they were all bought in India only.
Okay.
Yeah.
Krishna Raj Adhikari asked, why did you choose built-up box section for arch rib? Edge section is also possible, or was it not possible? Edge type section or any other section, why box section? Or channels back-to-back type arrangement
So
or
basically,
front to front, yeah.
like edge is also possible, but a box section has much more resistance to the buckling effects. Like it draws less second order moments compared to edge section. So that's the primary reason.
Okay.
Yeah.
Then uh, how much was the counterweight? Did you use any counterweight during launching?
No, there was no counterweight that was used during launching.
Okay. Harbhajan Singh asked a question about the cost. We have said it's around 15 to 20% of the cost of the main structure. Correct? He
I
wanted
think
the
so. Yeah.
cost per kg of the structure, but it's roughly 20% of the cost is what we can now say. Is the hangar design similar to tied arch bridge?
Yeah. Like hanger,
Okay.
if we look
Mr. Rajiv
from the
Ahuja
hanger itself, yes,
asks,
it is similar.
yeah, then Mr. Rajiv Ahuja asks, was any possibility of strong wind speed considered in the launching scheme? That is adverse wind condition during launching. And of course, you had your winches, side winches to
Yes, yes. So I had
side
already,
guys to hold it. Yeah,
yes,
lateral
yes. So I
guys.
explained like I had my side winches installed transfer direction on the other side so that if there are strong winds and arch tries to, sway, then though they will control its movement.
By those additional lateral winches for wind, yeah, for taking
Yeah.
care of wind swing. Okay. Okay, Sinja, what are the maintenance plans proposed for this bridge? In effect, it's in a remote area. What maintenance? Is there a structural health monitoring system?
Yeah, so basically, we have some sensors installed which give this the stresses in all the members, which can be monitored. The tension, the sensors also give the tension kind of in the hangers also, which can be
Right.
monitored. And again, there like the routine inspection of all the welds and the hangers is also proposed.
Right, right. Now, Sanjeev Mohan asked about the effects of temperature, everything being steel, and across the season, were there temperature variant, diurnal, seasonal, and how did they affect your launching? Were they a consideration?
So basically, let's like the temperature was taken into the design of the arch itself, both the seasonal variation and also the variation across the section of the arch, and it was one of a governing factor for the design of the arch itself. But if we see this the launching system, essentially these are just ropes and axial members. So basically,
Right.
with like they will not have any major variation effect through their cross section, but yeah, their length might slightly increase or decrease because of the temperature. So
Right.
yeah, that was not really a big problem, and
Right.
that will just change tension slightly. We had margins in the tension, so we did take care of that in that way.
Thanks. So it could be taken care during the
Yeah,
launching,
yeah, yeah.
managing the temperature through the system. Yeah. Now, someone asks, can you share the materials for design of network tied arch bridge in general? So I would suggest to all, his email is available, and this video is recorded. So the last slide has his email address. You are most welcome to write them and correspond to them for any further knowledge that you want.
Yeah.
Of course, I'm sure Deepak and his team will help out with that.
Yeah, and you can search for network arch per tweet, and you can get, he has some 26
Yes.
page kind of thesis or something, which you can study to get a basic idea about the system.
So in a way, this bridge is a tribute to Pertwee.
Yeah.
He's
Because
no
when
longer
we
with
started
us.
this bridge, we kind of mailed to him like we are going to build something like that, and he was very old at that time, and
But
the
he was
bridge
an
was
IABSE
launched in
member,
April. Huh?
He was an IABSE member for.
Yeah. So basically, in 1960, he had done the thesis on network arch, and so he said like he's not like really able to review things and something, but no, his blessings are with us. So we launched the
Yeah,
bridge in April, and
let's pay tribute to a good engineer, a great
yeah,
engineer. Yeah.
yeah.
Good. Now, some other few questions before we wrap up for the day, which I'm sure uh, you know, what are your key takeaways and learnings that would you repeat this? Is there some similar project in which you're using this concept now that you've got confidence in it? Is this something which you can use in hilly mountain areas where you cut back on the hill slopes and you use this unique system you have developed? What are the learnings and can it be repeated? Is it a repeatability situation or not?
Yeah, so basically, one of the key learning was like since like there is a basic difference in the philosophy when you are doing a detailed design and when you are doing enabling design. The enabling design factors tend to be slightly higher. But when I had designed the system, basically I was very concerned about the economy because the contractor had not really taken it into account when he had initially quoted. So my safety factors were of the order of what you keep in detailed design.
Right.
So yeah, so that gave us a bit of sleepless nights at times. So maybe in future I will keep slightly higher safety factors. And the
Right.
second thing is like if similar kind of thing is there, like similar terrain setup is there, and we cannot do thrust arch and we have to do tied arch only. Then I think this is one of a repeatable method because everything over here can be reused.
Yeah,
And
we look
we
forward.
are also doing another 175-meter network arch, but that happens to be a thrust arch. So over there, we are using these towers and these cable crane just for erection of the arch. But the other philosophy will be very different. Like that will also be kind of unique for network arches. Maybe again, the first for how a network arch is constructed in that way. Yeah.
Yeah. Right. So this webinar is going to be recorded. I again repeat to you all, this webinar will be recorded on the iabse.org/e-learning, e-learning /webinars. So iabse.org/e-learning/webinars. And you'll find this and many such presentations available for free to you. One last question, Deepak, before we close for the day, is did you design everything in-house? Did you need to get some assistance from a rope manufacturer like, say, Usha Martin or anyone like that? Or how did you go about that part? As you were a novice in this and you didn't know about it a
Yeah.
priori, how did
Yeah.
you then do this?
Like I did like everything was designed in-house only.
Right.
Didn't really, like since this method has not been used for bridges, I like really could not find some reference where this method was used, and maybe I can get in contact with somebody. And I thought like I didn't know any ropeway expert. So everything was designed with, let's say, common sense and first principles only. Like being an engineer, uh, let's we have to transfer forces to the ground. So how will they go? Design accordingly. So that was the philosophy that was used. Only no, the properties of the rope and everything were taken from the manufacturers, like what is their E value and braking load and everything like that. Rest everything, yeah, in-house.
Our young engineer Jatin Singla asks, any uplift seen on the other side of the bridge while launching, as deflections at tie side give rise to uplift at the other side. And Jatin, as
So
is a key person of our IABSE Young
okay.
Engineers Forum of India. He represents India in the EC, and he's a very, very active and been very active with our New Delhi Congress and continues to be active in the national group of the IABSE. So we
Okay.
welcome his question. Can you reply that?
Yeah, yeah. So basically, if we just see, this arch is supported at 4 points always. Like there are two supports at the back, and there are two supports in the front. So if something supported at 4 points, there is no question of uplift. There will always be reaction on those 4 points. Like I am not using a launching nose and a counterweight where there is a tendency of the back of the arch to uplift. It is just you are moving something on 4 points, keeping it kind of horizontal. Even if it is not horizontal, it has some inclination up and down. Still 4 points, there will be no uplift.
Right.
Yeah.
Right. Thanks for explaining that. And Mr. Prakash Fatke again asks, is there any health monitoring system to be installed on this bridge or during erection? Did you need anything to measure deflections, or was anything monitored whilst you, or just simple leveling instruments and things? How did you monitor anything, or there was no need
So for
at
the
that
bridge,
time and in
like,
the future?
yeah, for the bridge, we did not monitor anything, because for the bridge, this was not a governing design case. For the launching system, yes, it is. But for the bridge still doesn't have its deck. It is just the steel formwork. The load is very limited, and as I said, the bridge is always supported on 4 points. So it is like it is no just it is on the ground. For this, it is the same situation on the ground, or let's say 2 point on the ground and 2 points supported from below. So not really a governing criteria for the bridge during the launch.
Right. Thank you, Deepak. We are more knowledgeable today with your presentation, and we appreciate the innovation that you have put into this launching scheme, which is quite unique, and presented to us today. Thank you very much to you and your team, and we wish you all the best always, and look forward to active participation in IABSE's activities. Join some of the task groups. To all people in the audience, there are task groups of the, say, anyone can apply to join with a letter and your CV. There are so many activities that are happening. There's the e-learning board with a lot of resource material. You will find other network arches similarly like this discussed elsewhere in videos. You will see that in the e-learning. You will also see that the awards that are given every year, we should apply for awards. The Indian National Group should apply for awards. So should any national group. We encourage the awards every year in November. We give away a number of awards for people and projects, as well as for large projects, small projects, pedestrian bridges, best paper, and so on. There's so many. You look at the website, and
Sure,
you will
sure.
see that we're now open to accept for awards. So I wish the IABSE membership. I want you all to become members of IABSE, those who are interested, and learn and grow. For young engineers, it's very, very subsidized for what you get. And even otherwise, it is reasonably not so expensive to be a member of IABSE. But you get a lot back in return. You get a lot of knowledge, a lot of interaction, and personal agenda for growth. You will address that as a young engineer. That's what I would hope to see young engineers coming and joining IABSE and taking the charge ahead. Just as you've demonstrated, you do it. That's what you do. Now,
Yeah.
do it with the globe, do it with the body, do it with the IABSE, do it globally, and showcase your work too there. So a
Sure.
good couple of papers should be possible from this. The SCI journal will look forward. Venkat Hegde
Um,
and Luke Bhowmick are esteemed members of the Indian National Group, are both on the SCI editorial board, and Brinda is our publications manager. So in front of them, I'm asking you to make some good papers and go in more detail and provide some aspects of the modeling and so on and so forth, technical work. And I expect those papers to be submitted in the near short term.
Sure, sir.
Before you forget.
Yeah, no, I won't forget. I will do that.
Right.
Yeah.
On that note, before we close, Brinda, can you say a few words? Brinda, Firat, can you all both come on screen? Let us appreciate who you are, if you all are still present. Brinda, Firat.
Thank you very much. Thank you very much, Deepak, for this wonderful presentation, and Harsha for hosting this webinar on behalf of Indian National Group. And we look forward to your collaboration and cooperation. Thanks a lot.
You're
Thank
welcome.
you very much again.
With
Yes.
everyone.
Thanks, Firat. Thanks, Brinda, for being with us and making this happen today. On that note, shall we close this? This is evening in India. Elsewhere, it may be morning, it may be
Afternoon,
afternoon, but at least in India now it's past 7:30, nearing 8 o'clock. And I wish you all good night from India. Have a good evening ahead. And those who are elsewhere, have a pleasant day. Thank you very much.
Thank you, everyone. Thank you so much. Thanks to all the audience.